In this video, I just want to do a quick review of some of the main intuitions from calculus about derivatives, what they are and what they tell us about our functions, and how that can be useful in modeling specifically in population biology. And I'll say right at that beginning, I'm not going to do a lot of detailed derivations and proofs and stuff, so if you'd like to see more details about the underlying math parts, there are plenty of great resources and links on the website out to places like Khan Academy and other great math resources. Derivatives are all about rates of change. In population biology, we care a lot about population growth, which is, if you think about it, the rate of change of population number with time. So let's say I have some function that describes the number of individuals in my population over time. So I've got n of t with respect to t. If I can take the derivative of my population number, I get population growth rate. So let's say, for example, let's say I happen to have a population that's increasing linearly with time, straight line. And I want to know my population growth rate. What's the derivative of a straight line? Well, it's the slope, and it's the same at every point. My derivative is just the change in n for the change in t, which is the same everywhere, which is just rise over run. But what if my population isn't growing in a straight line? Or isn't changing in a straight line, I should say, because most of the time it's not. What if my population number is increasing in a curvier way, like this? And I want to know the population growth rate at a particular point. Let's say here. So at a point in time, I'm going to call time A. Well, I know that at this time my population is going to be n of A, and my population growth rate is going to be the slope of a tangent line to the curve at exactly that point A, because it's an instantaneous rate of change. But how do I get at calculating it? How do I find out what the population growth rate is at this particular point? Well, for starters, I can get a reasonable approximation by taking the slope of a secant line close to my point. So I'm going to take a secant line is when you take 2 points on a curve, draw a straight line between them, pretend that's straight, and you can see the slope of that secant line is going to be kind of close to the slope of the curve where they overlap. So the slope of my secant line, I should define my other point here. So the other point on my secant line is going to be at time A plus some change in t. So this distance, right, is the change in t. And the value of n at that point is going to be n at A plus the change in t. And this distance is going to be the change in n. So the slope of that secant line is just the change in n over the change in t, which is going to be on top, we've got n at A plus delta t minus n of A, and the change in t was just A plus delta t minus A, which we can just write as n at A plus delta t minus n at A all over delta t. So the obvious way to get an estimate of my instantaneous slope is to just make delta t smaller and smaller and make secant lines closer and closer to A, such that, as you can see, you can sort of see, it's a bit tiny, but the closer I make my second point to the original point, the more similar the secant line and the curve become, such that if we can get delta t so small that it's effectively the same as A, then the secant line and the curve will be the same, and we can get the exact instantaneous rate of change. That's the fundamental intuition of calculus, is that at this infinitesimally small delta t allows us to get the exact rate of change at a point. It's the part that sort of blew my mind when I first learned it in high school, but I should actually write it down instead of just being excited. So, the definition of the derivative, which I'm going to write as n prime of t for now, is a limit as the change in t goes towards 0 of this stuff over here. So it's the limit of the slope of our secant line as delta t goes to 0. And this blew my mind when I was a kid because I couldn't stop thinking about that difference. When delta t is 0, then it's just equal to a, and this whole fraction would be undefined. But if t is infinitesimally small but not 0, then a sort of magical thing happens and we get an exact estimate of the slope of the tangent line at that point. And it led to my adolescent self having all sorts of musings about whether or not the entire universe had to be discrete or could possibly be continuous. Anyway, so aside from this mind-blowing truth about the universe of lines, I should point out that there are lots of other there are other notations people might use. N prime is handy, prime notation is handy when you're dealing with functions of one variable, like t is the only variable that I have here that I could take a derivative with respect to. But if this was a multivariable equation, then maybe I could be taking derivatives with respect to more than one thing. So you want to specify that this is the change in n for every change in t. I like this kind of notation better. It's Leibniz notation, and it makes it more clear to me what function is having its derivative taken with respect to what parameter. Okay, great. So now we've reminded ourselves about the fundamental theorem of calculus and what a derivative really is. Now I want to talk a bit about what it means and what it can tell us and how it can be useful. In the case of population growth, it's fairly obvious. If we know population growth is the derivative of population size, and population growth is fundamentally interesting, we want to know its magnitude and direction. Is population growth positive? Is it negative? Is it 0? Is it stable? So knowing the value of a derivative is of fundamental importance quite often in population biology. In particular, we learn a lot about finding about points where the derivative of our function is equal to 0. I'm going to do a little demonstration of what I mean. So I'm going to plot a function here. I'm going to have this be time, and this is going to be n again. And I'm just going to pretend this is the number of fish in a school of fish, because I like fish. And we're going to say our school gets bigger, and then it gets smaller, and a bunch of stuff happens to the school of fish. Maybe something's chasing it and it gets bigger, and then things start eating it and it shrinks. Whatever. So first, we can learn a lot by thinking about the derivative in terms of its direction. Like, for example, I can tell by looking at this part of the function, the slope of the function here, the derivative, is positive, definitely. So it's increasing. Positive. And over here, the derivative is negative because the population is shrinking. And over here, it's definitely positive again, because our population is growing, and then it's negative again over here. An interesting thing is that if the derivative is positive over here and negative over here, that implies there must be a point where n prime is equal to 0. And another one over here, and another one over here. So if dn by dt is equal to 0, if it's 0 for a long time, that's what we call stable population growth, because the population is neither growing nor shrinking. But if dn by dt is 0 for a very short interval of time, then it's a critical point in our function, which is usually some sort of maximum or minimum. Down here, where n prime is equal to 0, this is a local minimum. And over here, where n prime is equal to 0, we've got a local maximum and then the global maximum of our function over here. You can have, as we can see here, you can have lots of maxima and minima within a function, but only one of them can be the global maximum. Right. So if I wanted to know, over the course of this time interval, what was the maximum population size of my school of fish, I would take my derivative of n of t, find the 0 points, and establish which one is the global maximum. So if it's not immediately obvious like this, you might have a more complicated function. If you want to know whether a critical point is a minimum or a maximum, there are several tests. I'm not going to prove them to you, but just it helps to remember. If you're not sure if a point is a minimum or a maximum, you can take the derivative of your function again. So in that case, that would be n double prime of t, or sometimes we write it d squared of n over dt squared, the second derivative, which is the derivative of the first derivative. And if the second derivative is greater than 0, then that point is a minimum. And if d and dt, if the second derivative is less than 0, then it's a maximum. So the basic intuition of the derivative turns out to be really, really important in population biology because it comes up all the time. Growth rates tend to be derivatives. They pop up all over everywhere in population biology. We might want to know the growth rate of a population. We might want to know the growth rate or the rate of spread of an invasion or an epidemic. Or the rate of spread of an allele in a population of genes. Derivatives also come up in population biology quite a lot when we're talking about sensitivity analysis. Now, the sensitivity analysis, most people think of, sure, how is my variable of interest going to change as I change something else about the model, which fundamentally sounds a lot like the rate of change of one variable with respect to the change in the other, which is just a derivative. Doing a sensitivity analysis always amounts to taking the derivative of your function of interest with respect to some other parameter. And the other major thing with derivatives that will come up is optimization, finding those local maxes and local mins. I might want to know, might want to find my optimal foraging strategy. I might be trying to optimize harvest or sustainable yield from a population, and you'll see plenty of other population biology examples in the homeworks that go with this module.